So my dear student, after obtaining the kinetic energy of the flywheel, now we are supposed to go and see how can we derive the moment of inertia of a sphere. Now we are going to look at the way we can demonstrate the formula of the moment of inertia for a sphere here as we observe. So first of all, let us read our statement here. And our statement is said that the moment of inertia of a solid sphere and also a hollow sphere rotating about an axis through its center can be derived as follows. So there are several steps that we are supposed to follow when we are delivering the moment of inertia for a sphere. And here, the moment of the sphere is categorized into two parts. Now we are going to look for a solid sphere, for instance, this ball bearing, and also for a hollow sphere. Now, for a hollow sphere here, is like a football. Now, the sphere is looked like either a solid sphere, such as a ball bearing, or can be looked like the hollow sphere, such as the football. So when it try to rotate, there are several ways we are supposed to use so as to demonstrate the moment of inertia for this sphere. First of all, we are supposed to go and look that imagine we have the solid sphere, and that solid sphere trying to rotate about an axis through its center. That is what we are going to observe here. How can we obtain the moment of inertia for a sphere, for a solid sphere? That is, it is trying to rotate about an axis through the center. That is what we are going to observe here. So, my dear student, we are supposed to consider a solid sphere of mass m. Now, imagine we have the solid sphere, and also a solid sphere containing the mass m. As we observe, we have the solid sphere that having the mass m, and also the radius r. So that a sphere having the mass m and also the radius r, and it is trying to rotate perpendicular to the axis of rotation, whereby it trying on an axis PQ. Now that moment of inertia here, now that sphere, so the sphere tried to rotate perpendicular. It means to the axis of PQ that is passing through the center of. We should go now. We are going to see the figure that indicate these demonstrations. So now consider elemental disk of radius. On our sphere that is containing the mass m and also the radius r. It having the elemental disk of radius a. Now having the elemental disk of radius and the small mass dm of thickness. It involves the small mass m as we try to observe of thickness dy at a distance y from the center or of the solid sphere. Now, this is our figure 4.8 trying to explain how the solid sphere is rotating through the center perpendicular to the axis PQ through the center. That is what we are going to see our figure here that give more explanation how the solid sphere looked like. And we have been observed that it involved the elemental disk. Now it contains the elemental disk with the radius a and also the small masses of dm of the thickness dy. So as we try to observe here, we have our solid sphere with rotation axis. We have the solid sphere with rotation axis through its center. Now we have the solid sphere, and that solid sphere, as we observe here, this it is trying to rotate on an axis through its center. Kama tunavyojaribu kuona demonstration yetu kwamba tuna solid sphere, ile solid sphere inajaribu kuzunguka on an axis. As we see that we tried to see on our concept of the rotation of a rigged body, that most of the body of the solid object trying to rotate on its axis, as we observe like this solid sphere. Now on our sphere here, Inside the sphere, inside the solid sphere, we have the elemental disk as we observe. This is the elemental disk that involve the radius A. It involves the radius A. From this point here up to the cycle, up to the end of the sphere. It means any point of the sphere as we observe. And also, my dear student, having the center. The sphere having the center that lie on it, it is an axis as we observe here. So the radius from the center, the distance from the center to the mental disk, to the end of the mental disk here should be equals to r, and by imply the radius. But the distance from the center up to the point where the center of the elemental disk must be given equals to y. But on the elemental disk containing the small change of dy, as we observe here, it involves the small change of dy. We see the direction of the angular velocity, that the sphere trying to rotate perpendicular to the axis of PQ from the center of through its center. So after this one, my dear student, what we should do here? Now we are supposed to, from our equation number 4.29 here, the moment of inertia dl of the disk is given by this one. Now let us recall how can we get the moment of inertia. And we know that the moment of inertia should be represented by dl, di, because for a small change of the solid sphere, we consider only a small change. Now we should say that dl, di, which represent the small change of the moment of inertia, must be equals to the half times dm times the a square. This we focus for elemental disk, as we know that the elemental disk contain the mass which is equal to dm. Now instead of writing m, we should write dm times the distance. The distance of the elemental disk must be equals to a square. So this should be the question number 30 on our first topic here. And after this one, since dm is the fraction of the total mass, as we know that dm represents the fraction of the total mass as we observe of the disk. So the mass and the volume for for both sphere and the disk can be expressed by this one. If we consider the mass and the volume for both sphere, it means for that elemental disk and also the whole of the sphere, it can be expressed by the ratio. Now we should say that small change of the mass divided by the small change of the area. It means we are talking for the elemental disk and also the whole sphere. Now we should consider the ratio of the mass of the disk and the area of the disk, and also equals to the mass of the whole sphere divided by the volume. As we observe here that dm over dv represents the volume of the elemental disk. Now after this one, my dear student, what we are supposed to do here? The thing that we are going to do is to look for how can we get the volume of the sphere. Because on our formula we tried to see the ratio of the elemental disk, the mass of the elemental disk with it is the volume, and also the mass, the ratio of the mass of the whole sphere and also the volume. Now we should say that the whole sphere must involve the volume which is equal to 4 pi r cubed divided by 3. This should be the volume of the sphere. And after this one, for the small change of the volume here, the small change of the volume, it means we are going to look for the elemental disk. Now we say that the volume of the elemental disk must be equals to pi a square times the dy. We should take pi a square, then we times it by the small change of the elemental disk. This is how we obtain, my dear students. And after this one, we were supposed to substitute our given values. Now let us go and substitute the data that we have into our equation here. So we should go and paste here, make a dm at the subject, the mass of the elemental disk, which is equal to dm must be equal to m, this mass of the whole sphere. Then we divide it by the volume, we times it by the volume of the elemental disk. Then after this one, my dear student, if we substitute the value of the volume here, which is equal to 4 pi r cube divided by 3, and also the dv, which is equal to pi a square times dy. Now we obtain that the dm must be equals to 3ma square. Then we divide it by 4 r cube. This should be our value times dy. Now we have obtained dm. Now the thing that is required here is to go to substitute into our di, as we try to see that di must be equal to dm times to the a times to the a square. Now we should go and proceed for the next session. So by saying that, my dear student, now this is the end of our session here. I would like to invite you again for another session. I wish you all the best. Have a nice moment. Thank you.